Hello, my name is Ashley, and for the past couple weeks I've been working as assistant in Dr. Anderson's research group here at the University of Toledo. My mentor's project focused mainly on the concept of chirality. A chiral molecule is not superimposable on its mirror image. To be superimposable, the object's mirror image cannot be placed on top of the original object and have all of the parts coincide. For example, your hands are chiral because your left hand's mirror image is simply your right hand. In addition, if you placed your right hand over your left hand, the parts would not match, no matter how much you turn or rotate your hands. This is why chiral objects are said to possess handedness. Here's an example of a chiral molecule called ibuprofen. Many of us may be familiar with one of its trade names, Advil, which is used as a pain reliever. This is said to be chiral because if its mirror image were to be placed over the original image, all the parts would not coincide. These two molecules are called enantiomers because they're a pair of two chiral mirror images. Also, chiral molecules tend to have chiral centers, which are usually carbons. Right here is the carbon center of ibuprofen. A chiral center must be bonded to 4 different groups. This particular carbon is bonded to a hydrogen, a methyl group, and 2 other carbons which are bonded to different groups. This one is bonded to a carboxylic acid functional group, whereas this one is bonded to a ring structure. It is worth mentioning pharmaceutical drugs because the concept of chirality is quite important. After separation of a chiral pharmaceutical drug, one is assigned either S left or R right. This is done by using the atomic numbers of the elements in the molecule. In this example, we'll use this molecule which has hydrogen, fluorine, a methyl group, and bromine. First, you start visualizing the group that has the smallest atomic number. In this case, hydrogen has the smallest atomic number, so we'll hold it away from us. Since bromine has the greatest atomic number with 35, that is our starting point. Then you look at the other 2. Which one has the next highest atomic number? Fluorine or the carbon in the methyl group? It's fluorine because its atomic number is 9, whereas the carbon in the methyl group is 6. This molecule is assigned R because we're rotating it clockwise from the highest to the lowest atomic number. I mention this because when the drugs are separated, you can then determine which enantiomer will be used for a particular drug. One enantiomer could be helpful to the body, whereas the other one can have no or even harmful effects. For this research, we extract chiral molecules by headspace solid phase microextraction, or SPEME, and then separate them by gas chromatography, or GC. The example I will show you right here is 1-chloryl-2-propanol. Now let's go to the lab and start our extraction. This is my fiber that I use for my extractions. Now I'm going to place the syringe into the sample. The analytes partition to the coating for the fiber for about 5 minutes. The tip is exposed to a high temperature in the GC so the analytes will come off. Now that the extraction is over, we can quickly take it to the GC so the analytes can come off. Now that the run is over, we can see that the chromatogram shows a separation of the chiral molecules through the use of peaks. As you can see here, this is the 1-chloryl-2-propanol, and these 2 peaks right here are the derivatized product of it. It is extremely important to tell which one is R or which one is S so that one could know which one is helpful to the body and which one can have no or even devastating effects. It is worth mentioning because during the 1960s, pregnant women were taking the sedative thalidomide. It turns out that the R enantiomer helped these women, and unfortunately the S enantiomer caused devastating birth defects. So next time you prescribe drugs, or even when you take simple cough syrup, think about the concepts discussed today. Without chirality and its relevance to pharmaceutical drugs, many medicines on the market probably wouldn't even exist. I would like to thank the Project SEED program of the American Chemical Society and the National Science Foundation for funding my research. I hope you learned a lot of new concepts in today's video, and thanks for watching.